So now we look at circuit parameters, and we start to be reintroduced to some things that we've seen before, only in a little different form. So we learned from Ohm's law that conductance, resistance are reciprocals, and a term susceptance and reactance are reciprocal. So we've used the resistance and the reactance. Susceptance is something that we haven't used a lot. We also have admittance and impedance. So we're looking at inverses here and how we can use inverses or reciprocals to help us to solve problems. This comes down to sometimes it's easier to use these inverses or receptacles on certain types of circuits. So conductance and susceptance and admittance are parallel circuit parameters. Resistance, reactance, and impedance are series circuit parameters. So the idea behind this is using these reciprocals to help us solve for specific type problems more easily. So if we take a look at this formula below here for capacitive susceptance, it looks kind of like what we saw before for the X sub L, the reactance for an inductor, since it's in the numerator. But yet it has the term that was in the denominator for reactive components for capacitive reactance. So we can see here the evidence is that we have inverted 2 pi fc and called it now capacitive susceptance, or the B sub C. So let's put it to work and see how we use it in these circuit analysis and parameters. So now if we have a resistance, 3.3 k ohms, a capacitance of 75 nanofarads, and our operating frequency set at 500 hertz, let's solve for the conductance, the capacitive susceptance here, the admittance Y, and the phase angle. And they want us to express Y in a rectangular and polar form. Like I said, in every case, you're going to see us solving it in both forms so that we get used to it. So now using that inverse formula, B sub C is equal to 2 pi fc, we plug in our relationships into the relationship, our knowns, 500 hertz, 75 nanofarads, and we come up with 236 microsiemens for B sub C. Now if we look at the relationship for conductance, since we know conductance is the inverse of resistance, 1 over R, then we can put our resistance, 3.3 k ohms, into the conductance formula, and we have 303 microsiemens. So we can take both of those terms now, both of those values, and they become the rectangular representation for our admittance as 303 microsiemens plus J, 236 microsiemens. So that should be divided there. I don't know why that didn't do it, but we'll go ahead and clean that up now. So now we can see how we're using some of our other values here to help us solve for these circuit parameters. Okay, so now just like we've done before, let's take the tangent of theta relationship. Since it is B sub C over G, both are values that we have, we put them into the ratio, the quotient, and we get a value of 0.779. That value then, taking the inverse tangent, gives us a phase angle of 37.9 degrees. So again, now we need to switch to another trigonometric function that allows us to solve by using what we know. So in this case, the problem asked us to solve for Y, the admittance, and we can take it and turn our terms around so that we now have Y is equal to B sub C over sine theta. And we can put those values into the ratio here, and we get a value of 384 microsiemens. So in polar form, 384 microsiemens at an angle that we solve for, 37.9 degrees. Let's look at another example here where we have R equal to 680 ohms, capacitance equal to 100 nanofarads. Now we have an operating frequency of 5.5 kHz. We have a total current of 25 milliamps. Now we have a host of values they want us to solve for. G, B sub C, Y, theta, I sub R, I sub C, and the voltage. Again, express Y in terms of rectangular and polar forms. So if we start with our relationship, B sub C is equal to 2 pi FC, we get 3.46 millisiemens. Again, we use our relationship for conductance, and we get the inverse of 680 ohms, or 1.47 millisiemens. Now we have the terms that we can put into the rectangular relationship. 1.47 millisiemens that we just solved for, 3.46 millisiemens on the j-axis that we solved for. Again, taking our values to solve for the tangent of theta, we end up with 2.35. When we use our two terms, taking the inverse tangent, we get a phase angle of 66.9 degrees. Again, starting with the sine of theta, moving the terms around so we can solve for y. Y then is equal to B sub C over sine theta, which gives us 3.76 millisiemens. So we can take those values then and put them directly into the y polar form, 3.76 at an angle of 33.3 degrees in millisiemens. To solve for the current, since we had the magnitude of the current, 25 milliamps, we can plug that in. We already know what our phase angle is, 66.9. That gives us the polar relationship. If we want to solve for the current through the resistor and the capacitor, then we have our relationships that really started off as the definition of cosine theta. Cosine theta in this case being IR over IT. We manipulate the terms around and we get a current of 9.79 milliamps. We do the same thing for the current through the capacitor. We get 23 milliamps. So if we take IT, I total, divide it by Y, the admittance, we get our voltage applied as 6.66 volts. You'll notice over here in the representation, we've got this little arrow inside of a circle. That's the representation for a current source. We've seen in others the representation for a voltage source. So that current source actually has a voltage value of 6.66 volts. So with that, we will come back and look at circuit currents in the next section.